So in the second part of 13.3 we will talk about curvature. So first of all, what is the concept of curvature? The curvature tells us how sharply a smooth curve turns, right? In other words, it tells us how abruptly the curve changes. So if we have something like this, right, just by from intuitive point of view, we can conclude that at this point, right, the curve turns way more sharply than, let's say, at this point right here, right? And then later on we'll point out that this is closely connected to this idea here that we can measure or describe the curvature by describing how big, sorry, maybe something like this would be more, this circle would be more appropriate. What kind of circle can describe, can hug the curve at that particular point, okay? So for example, if we have a curve, let's say something like this, in and if we want to measure the how sharply, how abruptly this curve changes at this point, let's say here, right? If we point a few, if we sketch a few unit vectors, let's say something like this, okay? And then if we look at the curvature of the curve right here, we can see that here the unit tangent vector doesn't change as abruptly at this point here. And that coincides with the intuitive idea of curvature, that the curve is curvier, right? It changes, the curvature changes more abruptly here rather than here. And then here again, it starts changing abruptly, which can be seen by the change in the unit tangent vector. And that is exactly how we will define the curvature. The curvature is going to be defined as a, let me just play with the light here, maybe. Yeah, something like this should be better. Oops. Sorry about that. So we will define the curvature as the magnitude of the change of the unit tangent vector with respect to the arc length. And you may ask, well, why with respect to the arc length? Because the arc length is independent of any parameterization. That's why we take the change of the unit tangent vector with respect to the arc length, okay? Now, let us think about what this formula asks us to do. It asks us to reparameterize the curve with respect to the arc length, then evaluate the unit tangent vector, find the derivative of the unit tangent vector with respect to the arc length, and find the magnitude. Where is the problem here? Well, we mentioned in the previous lecture, the first part of 13.3, that the reparameterization with respect to the arc length is not always possible. First of all, because solving that interval is not always easy, and then finding a relationship between S and T is not always straightforward. So our goal now is to figure out a better formula for the curvature. So let's remind ourselves what was the unit tangent vector. The unit tangent vector was r prime over the magnitude of r prime, okay? Then if I evaluate the derivative of the unit tangent vector with respect to t, where the unit tangent vector is parameterized with respect to the arc length, that's going to be dt ds by the chain rule times ds dt. And from here, just make sure we want to find how much is ds dt. Well, sorry, dt ds. Well, dt ds is going to be equal to, this is the product rule, so it's a product, sorry, the chain rule, so this is a product, so dt over ds dt. Okay, now we said that the curvature is the magnitude of dt ds, which is the magnitude of dt over ds dt. Now let's stop here for a second and remind ourselves again that we proved that ds dt is equal to the magnitude of r prime. So instead of ds dt here, I'm going to write magnitude of r prime, right? And then dt is the derivative of the unit vector with respect to t, so that's t prime. Finally, this can be just written as the length of the magnitude of the derivative of the unit tangent vector over the magnitude of r prime, right? Sometimes for magnitude we put 1 bar, like in the book. Sometimes we put 2 bars, but that's always the same. It just depends. What kind of notation we're going to adopt. So one more time, let's just confirm that we will find the curvature by using the formula magnitude of t prime over magnitude of r prime. Okay, so let's do an example. Find the curvature k of t for r of t being defined as, I have space here, so for r of t defined as sine of t cosine of t sine squared of t and t. Okay, so the first thing that I want to find is the unit tangent vector. So r prime is equal to the derivative of each component. Be careful here, I have to use the product rule. Derivative of sine of t is cosine of t. Cosine of t times cosine of t is cosine squared of t, plus the derivative of cosine of t times sine of t. Derivative of cosine of t is negative sine of t times sine of t, negative sine squared of t. For the second component, the derivative of the second component, I use the chain rule. 2 times sine of t times derivative of sine of t, which is cosine of t, and derivative of t is just 1. Okay. Now here you have to be careful to recognize these two identities. Okay, cosine squared of t minus sine squared of t is cosine of 2t, and 2 times sine t cosine t is sine of 2t, and that is going to make our computation way easier. Okay, now let's find the magnitude of r prime. Why? Because t is equal to r prime over the magnitude of r prime. So I need to find the magnitude of r prime. That's the square root of cosine squared of 2t plus sine squared of 2t plus 1 squared This is just the basic elementary trigonometric identity, so that's 1 plus 1, or that's square root of 2. So we can find the unit tangent vector is 1 over the magnitude of r prime, so that's 1 over square root of 2 times r prime, which is cosine of 2t, sine of 2t, and 1. Okay, again, what was the definition of the curvature? K is equal to the magnitude of t prime over the magnitude of r prime. I have already the magnitude of r prime, that means that I have to find t prime and find its magnitude. Okay, so t prime is equal to, the constant stays outside, derivative of cosine of 2t is negative 2 sine of 2t, derivative of sine of 2t is 2 times cosine of 2t, derivative of 1 is 0. Okay, and now let's find the magnitude of this vector. The magnitude of t prime is equal to square root of negative 2 sine of 2t squared over square root of 2 squared, which is 2, plus 2 times cosine of 2t squared over square root of 2 squared, which is 2. That's equal to square root of 4 times sine squared of 2t over 2 plus 4 times cosine of 2 squared of 2t over 2. Cancel these two. I get square root of 2 sine squared of 2t plus 2 cosine squared of 2t, factor 2, factor out the constant 2, and you get sine squared of 2t plus cosine squared of 2t. Again, this is just 1, so I get that the magnitude of the derivative of the unit tangent vector is simply square root of 2. Once I have that, I come back here to the definition of the curvature, and I have that magnitude of derivative of the unit tangent vector, we just evaluated was square root of 2. Magnitude of the derivative of the vector is square root of 2. So in this case, the curvature is constant 1 for any point on this curve. Okay, so let's do another example. Example number 2. Find the curvature of a plane curve defined by r of t is equal to a cosine of t, a sine of t. Now you should be able to recognize this curve. We've mentioned this one many times. The components here are x cosine of t, y is equal to a sine of t, and from here x squared plus y squared is equal to a squared cosine squared t plus a squared sine squared t, which is equal to a squared, and x squared plus y squared is equal to a squared is the definition of the circle centered at the origin with radius a. Okay, so let's see what is going to be, what we can figure out about the curvature of a circle, right? Again, first find the derivative, negative a sine of t, a cosine of t. Find the magnitude of the derivative, a squared sine squared t plus a squared cosine squared t, that's square root of a squared, which is a. Right, you can say that here a is positive. Okay, that gives us the radius of the circle. Then the unit tangent vector is r prime over the magnitude of r prime, so that's 1 over a negative a sine t, a cosine of t, or simply t is equal to negative sine of t cosine of t. Okay, now we have to find the derivative of the unit tangent vector, that's negative cosine of t sine of t, and its magnitude square root of cosine squared of t plus sine squared of t, that's equal to 1. Okay, So finally, the curvature of a circle with radius 1 is equal to 1 over the magnitude of the derivative of the vector is a, 1 over a. Okay. So what does this say? It says that the curvature is equal to 1 over the radius of the circle, or in other words, the smaller the circle, the bigger the curvature, right? This circle has bigger curvature than this circle right here, right? And now you can have some kind of mental experiment with this and send a to infinity, and it's just going to hopefully confirm your intuition that if the radius goes to infinity, the circle is going to be so big that it's going to flatten out. And it flattens, if it in terms of the curvature, if you send a to infinity, 1 divided by something that goes to infinity goes to 0. So the curvature is going to approach to 0. Now we're going to come up with another formula for the curvature. So we're going to show that the curvature of a vector function can be expressed as the magnitude of the cross product between r prime, r double prime, over the magnitude of r prime cubed. Okay, so let's see that. Just a reminder, t is equal to r prime over the magnitude of r prime, and the magnitude of r prime is equal to ds dt. Okay, from here r prime is equal to magnitude of r prime times the unit tangent vector, and from this formula right here I can write that this is equal to ds dt times the unit tangent vector. So r prime is equal to ds dt times the unit tangent vector. Okay, then the second derivative is going to be equal to the second derivative of s with respect to t plus, using the product rule, ds dt times t prime. Okay, now if we do the cross product here, r prime cross product r double prime will be equal to ds dt times t cross product second derivative of s with respect to t times t plus ds dt times t prime. Okay, so we've talked about properties of the cross product. This is going to end up being ds dt t cross product the second derivative of s with respect to t times t plus ds dt times t cross product ds dt times t prime. So let's stop here for a second and let's discuss why this product is going to result with 0. Well, remember that any vector cross product itself is 0, and here I have t cross product t is equal to 0, so this whole part is simply going to be 0. That leaves us that r prime cross product r double prime is equal to ds dt squared times t cross product t prime. Okay, now let's figure out how much is this product is going to be how much. So recall that if the magnitude of a vector is equal to a constant, then the vector dot product its derivative is 0, or in other words, the vector and its derivative are orthogonal. Okay, now the unit tangent vector is a constant, it's 1, which implies that the unit tangent vector is orthogonal to its derivative. Now also remember the definition of the cross product is the magnitude of t times the magnitude of t prime times sine of theta, and because t and t prime are orthogonal, that means that the angle between them is pi over 2, which makes this part just 1, or the magnitude of t cross product t prime is equal to magnitude of t times magnitude of t prime. But the unit tangent vector is called unit tangent vector because its unit is 1, so this part here is 1, and we get that t cross product t prime is just the magnitude of t prime. Okay, so let me, on the last page we stopped at this point that the magnitude of r prime cross product r double prime is equal to ds dt squared times t cross product t prime, magnitude of this, right, which is equal to ds dt squared is always positive, so that's ds dt squared times the magnitude of t prime. Now if we divide both sides here by ds dt squared, we get if we divide both sides, right, by ds dt squared, we get the following equation. And finally we can refer to the formula about curvature that we know. That's the magnitude of t prime over the magnitude of r prime, which in our case t prime is equal to the magnitude of r prime cross product r double prime over ds dt squared over the magnitude of r prime. One more time, I'm going to remind you that ds dt is equal to magnitude of r prime, so this is just magnitude of r prime cross product magnitude of r double prime over magnitude of r prime squared times magnitude of r prime. And finally we get the formula that we wanted. So let's do an example. Find the curvature of the twisted cubic whose definition is r of t is equal to t squared t cubed. Okay, so using the formula that we had that we just derived, first I have to find r prime, which is 1 2t 3t squared, and r double prime, which is equal to 0 to 6t. Now the cross product between these two vectors, r prime cross product r double prime, is equal to, this is going to be 12t squared minus 6t squared I minus 60 j plus 2k, or r prime cross product r double prime is equal to 60 squared negative 62. Now we have to find the magnitude of this cross product. That's square root of 36t to the power of 4 plus 36t squared plus 4. Let's see whether we can simplify somehow this. We can factor 4 in the square root, and we have 9t to the power of 4 plus 9t squared plus 1, okay, which is equal to 2 times square root of 9t to the power of 4 plus 9t squared plus 1. Okay, the only thing that that's left is finding the magnitude of r prime. That's square root of 1 squared plus 2t squared, which is 4t squared plus 9t to the power of 4. Okay, that means that the curvature of this twisted cubic at any point t is equal to square root of 9t to the power 4 plus 4t squared plus 1, the whole thing to the power of 2. And I invite you to go online and try to find some interesting plots of this curve, of this twisted cubic. Basically, if you think about it, the components are x is equal to t, y is equal to t squared. From here, y is equal to x squared, and z is equal to t cubed, which implies that z is equal to x cubed. So basically, if you remember, this is going to be the parabolic cylinder, and this is the cubic cylinder. Okay, so basically this curve is the intersection between these two cylinders, right? So I don't know if I should even get into this. Okay, so this is the cylinder, y is equal to x squared, and then z is equal to x squared is going to be the point of the curve of intersection is going to look something like this. Okay, so as you can see, at the origin, the curvature is going to be 2, and then if you send t to infinity, sorry, at the origin the curvature is going to be 2, but as t goes to infinity, the denominator is going to grow to infinity much faster than the numerator, which means that the limit is going to go to 0, which means that this curve flattens out as t goes to infinity.